Happy Independence Day. Yeah, so this was unexpected, isn't it? Yeah, so we have freedom actually. We are not independent in all domains, isn't it? So still it requires much more effort to be independent, isn't it? So usually technologically, I hope you know that one. So around a couple of years back or 1 year back, so Delhi was the top importer of weapons in the world. So so during that time when I mean last year, I think, isn't it? Last year. So top importer. I mean we are spending a lot of money in order to purchase so technology, in order to purchase something. Of course, it is needed. So for national security, everything it is needed, but we are not independent technologically. So the best example for technologically independent country is Israel. They have robotic army in their border actually. Is that okay? So again, sometimes we scare of many things. One thing is again so threats, and for all of them, if we were technologically independent in all domain, we don't have to scare for anything usually. Is that okay? So still India has to purchase intercontinental missile interceptor. That is from Russia. Missile interceptor. Isn't it? So usually India will not go to war. I think past 1,000 years or something. So it has never went to war. Again, but we need to be defensive, am I right? Again, that intercontinental interceptor, I think, so that again it is purchasing from Russia, I think. Lot of things are purchased again. That's why. So it seems to be, again, we are not independent. We have freedom, but we are not independent. Okay, in case of nuclear technology also, in case of many other technology, we are depending on other countries. Okay, so that's why it needs your hard work and your contribution to make a technological independent movement. Shall I say like that? Just like a freedom movement or something, technological independent movement. So we need that one, okay? Yeah. So let us not divert again. Is that okay? So classical physics. Now let me start again. J.C. Upadhyay and Goldstein, okay? So you have to read Goldstein theory, and we shall start solving some problem from Goldstein. And I'm going to make one group so that we shall start solving Goldstein problem in that group, okay? Because there are no solution manuals for Goldstein. No solution manuals for Goldstein. And most of the problems are very difficult to, guess what he is expecting actually. And lot of problems in question paper, that is again from Goldstein. Not only here, even if you see MIT Princeton question, lot of problems from Goldstein only. Very standard text in classical physics, okay? In usually Lagrangian Hamiltonian technique. So lot of problem that is still unsolved, still I couldn't able to solve. So many people couldn't able to solve it, okay? So that's why we shall make one platform to solve that Goldstein questions. Okay, yeah, you can solve all Griffiths questions because there is a solution manual. Even if you couldn't, you can see that one. All Reef question, all other question, usually solution manuals are available. Or at least much solved problems are available. Suppose if you take Jetili, lot of solved problem. If you solve that one, you will not get that difficulty in solving outside problem. But Goldstein problems are little difficult to solve. I'm not talking about selective problem. So if you search for solution, there is one solution by Homer Reed from MIT. Again, he solved selected problem that you can also solve after the theory. I can also solve, okay? So again, we shall start solving so much more, from Goldstein. So in J.C. Upadhyay, you can solve all questions, no need to worry, okay? And he has given answers also. So that's the best way, okay? You better to solve JC Upadhyaya, read theory from Goldstein, so solve JC Upadhyaya, and I will discuss that Goldstein problem in the class. Is that okay? And JC Upadhyaya, he just copied Goldstein book. Okay. So usually sometimes sentence wise. So, but reshuffled. But questions are also from Goldstein. But he has given answers. That would be very better. Am I right? But little typing mistakes are there. Not little, many typing mistakes are there. So again, we need to point out that one. Okay. So now let me start with this one. Again, why we need a different approach other than Newtonian mechanics? I think you had something, this Lagrangian and Hamilton's approach, Lagrangian approach in degree. Am I right? You had that one in degree. Now, why we need this one? Why we need different approach? What's wrong with that? Our Newtonian mechanics, we can solve all problems, isn't it? So what? Lagrange's differential equation is also second order differential equation. Yeah, you need to do lot of vector analysis, vector algebra, isn't it? Because force, acceleration, velocity, all of those were vector quantity. Am I right? So that's why you need to do lot of vector algebra before solving the problem. Okay. And one more point here is, again, we need to discuss constraint. Then let me come to that point. Suppose sometimes you may not know all forces, what you call present in the problem. You can apply Newton's second law only when you know all forces. Am I right? You can apply Newton's second law, you can solve that one. Sometimes some part of those forces acting on the system, so that may be unknown, then you can't apply Newton's second law at all. Is that okay? So we can solve many problems from Newton's second law. There are some problems which can't be solved using Newton's second law. And there are many problems which are very difficult in that route, Newton's way. Is that okay? And that's why we are just transforming that vectorial to scalar thing here in a whole this Lagrangian and Hamiltonian technique. So one thing is, you don't have to do any vector algebra. Okay, you don't have to do any vector algebra. And one more thing is, sometimes if you don't know some forces acting on the system, then also you can solve the problem. And one more very important thing here is, you got evolution of the theory. Evolution means, I mean, you can proceed with this one after Hamilton's theory. So we have applied the same thing to quantum mechanics, statistical mechanics and all. Okay. So Newtonian mechanics was stagnant actually. Okay. So it was stagnant. I mean, so it had no evolution usually. So once you define Newton's second law, you solve that one, it's over. Okay. So but this approach, this have got evolution. Evolution in the theory happened. So even usually this Lagrangian, these things are used in field theory also. In the beginning of one of the approach of the field theory, so starts with this Lagrangian mechanics actually. Okay. So that's why there is a lot of evolution of the theory here in case of classical physics. Again, so in Goldstein chapter 1, survey of elementary principles, in that one he just discussed mechanics of a particle, again Newton's second law. Let me start with constraints. Okay, let me start with constraints. What do you mean by constraint? What do you mean by constraint? Restriction on the motion of the particle. Am I right? Restriction on the system or restriction on the motion of the particle. We call that one as constraint. Can you give me one example? Yeah. Particle moving in a one dimension. So that is also constrained. Why? It can't go to other dimension. Am I right? That is a constrained motion. Then, yeah, gas particle in a container. It can't. Gas particles are not allowed to go outside. Constrained, isn't it? Yeah. Then, yeah. Pendulum. Am I right? How pendulum is a constraint? Length is constant. Mass cannot move anywhere. Okay, it should move. Suppose if you have this one, so this mass can move. This mass can move only on this line. Am I right? Again, it's a part of whole circle actually. Am I right? Circular motion, that's also constrained. Am I right? So if you take origin, circular motion, mass m here, which is revolving about a fixed point. So then that's also constrained motion. It cannot go anywhere in the plane or it cannot go outside the plane and it should be restricted on the plane, it should move on that part. So isn't it? Now that constraint, again, a restriction on the system, and in many times, most of the case, we may not know that what causes that constraint. There should be some, again, force which should cause that constraint, am I right? We may not know that one sometimes. Okay, so then again, so it will be very difficult to apply Newton's second law actually. Okay, we call it one as forces of constraint. So in most of the case, we will not able to find what is that forces of constraint. Okay, so now, so due to that one, again, we are just transforming from Newton's second law. Again, just read out the book. There are a lot of other reasons why we are transforming. Now I have constraints. What are constraints? Restriction spelling? R-E or R-I? R-I? Restriction on motion of particle or system of particle or whatever. Okay, simply. Yeah. Now let us divide that constraint into two parts. One is holonomic, other one is non-holonomic. Holonomic and non-holonomic. So this holo means, I think that's again a Greek or some letter or Latin letter, okay? It means integrable, okay? Holo, the word means integrable actually, okay? So holonomic means, so you should be able to write constraint equation, okay? Equation representing a constraint. Suppose particle moving in one dimension, that's what you said, am I right? How do you define that one? How do you define constraint? I better to go for coordinate, am I right? You can define constraint only when you define coordinate usually, okay? Suppose particle moving only on x-axis, x cap, y cap, z cap. Suppose particle is constrained to move along x-axis. What is the constraint equation you write? Y equal to 0, y should be equal to 0, z should be equal to 0, am I right? Or y should be equal to constant, z should be equal to constant. That becomes one-dimensional motion, am I right? Y and z coordinate, so they are 0 or they are some constant, then that becomes one constraint motion. That constraint that says particle should move on only one direction, am I right? So that's an equation, am I right? This is an equation representing that constraint. What does this equation says? So move on straight line like that, isn't it? Yeah. So now similarly, suppose if you take a container, is that okay? So with one corner as the origin, and I have a particle which is moving on that one, okay? I have Lx, Ly, Lz as the dimension of the cube, is that okay? So now look at here, so your x position should be less than or equal to 0 to Lx, y position should be 0 to Ly, z position should be 0 to Lz, am I right? This is also constraint equation actually. Are you getting my point? This is also constraint equation. So this says it should be confined within the region of Lx, Ly, Lz. So a kind of rectangle, cubic rectangle in the region of Lx, Ly, Lz. Am I right? So that's also constraint equation. Okay. So now again you can take one more example. Suppose particle moving on a circle. How do you write constraint equation? Suppose this is the origin. So distance from the origin equal to constant. Am I right? Suppose if you choose xy plane at the origin, x here, y here, r equal to constant. Am I right? R equal to a, suppose. That is a constraint. Am I right? So I mean distance from the from a point is a constant. That is the meaning of the trajectory. Am I right? So circular trajectory. What do you mean by this r according to Cartesian coordinate? X square plus y square. Am I right? Can I write like this? If you choose this one as origin, that's equal to constant. X square plus y square is equal to a square. That's again constraint equation. Isn't it? That what does that equation says? Move on a circle with radius a, like that, isn't it? So now look at here. If equations have got equality, then that is actually holonomic constraint. If constraint equation contains inequality, then that is non-holonomic. Is that okay? Not only that, okay, so we have one exceptional article case, so that's mentioned here. So usually you can just define that holonomic constraint as, so can I just write that one? Constraint, yeah, wait a second, let me give some more interpretation. So again, before explaining that holonomic constraint, let me give some more interpretation. Now look at here. You had again 3 dimension, x cap, y cap, z cap, okay. So particle was moving in a 3 dimension, okay. Then what is the number of degree of freedom usually? 3. One particle which moves in a space, number of degree of freedom is 3, am I right? So now suppose I put this restriction, what is that one? Sorry, y equal to 0, z equal to 0. Let me put this restriction. What is this restriction? I mean, this is a kind of constraint, am I right? So what does this say? Move only on x-axis, am I right? So move only on x-axis. Is that okay? Now look at here. Once a particle moves only on x-axis, you don't need other 2 coordinates. You need only one coordinate, origin, am I right? Now this constraint reduced number of coordinates. You had 2 constraint equations. Initially, you had 3 dimension, am I right? Anything can be explained, one particle motion can be explained by 3 dimension, am I right? So now you had 2 constraint equation, it reduced 2 coordinates. And what you need only one coordinate to explain this motion, am I right? One dimensional motion, only one coordinate is needed. Okay. So, but look at here. Here also you have constraint equation. Will that reduce number of coordinates required? Are you getting my point? It will not reduce number of coordinates required. Now look at here. Yeah, this is again a kind of system where again this will help us to reduce number of coordinates. Can you explain how? Go to polar coordinate. Am I right? Go to polar coordinate. Now look at here. So let me just take this example. I have particle moving on a circle. Okay, y here, x cap here, y cap here. Particle of mass m moving on a circle. Is that okay? Usually we start with Cartesian coordinate. Most general, we start with Cartesian coordinate. Am I right? So x comma y, that is the position of the particle. But what is the constraint equation? Yeah, x square plus y square is equal to a square. Am I right? Now look at here. Yeah, this is a particle moving on a plane. Actually, I have to write one more constraint. What is that one? Z equal to 0. I mean, it should be on a plane. Am I right? So usually you start with 3 dimension. You got one constraint. So that avoided one coordinate. That reduced the number of coordinates required. Now you need 2 coordinates. Again, you have one more restriction. What is that one? X square plus y square equal to a square. Or this length equal to constant. That is a constraint. Okay, that's a restriction. That this particle should move only on the circle. Is that okay? Now look at here. So this is a kind of equality. Am I right? I said whenever we have a equality, you can call it one as a holonomic constraint. So not only that one, that is also not complete statement. So that equation should be able to reduce number of coordinate required. If the equation regarding constraint, if it what you call reduces number of coordinate required to explain the system, then that is holonomic constraint. Now look at here. How? Yeah, if this is holonomic constraint, this should be able to reduce number of coordinate. Am I right? Now you have 2 coordinate and one equation. You already reduced one. Okay, this is over. This part is over. Now you have 2-dimensional motion. In that 2-dimensional motion, again you have one constraint equation relating x and y. Can you reduce number of coordinate required? That can be done by going to transforming into polar coordinate. Again, that transformation is done by y equal to. So how do you draw that one actually? We call this one as initial line. Plane polar coordinate. Am I right? Initial line. So we are going to call this one as r. So this is as theta. And r equal to a is a constraint. And in case of polar coordinate, what do you mean by polar coordinate? Your point should be represented by r and theta. Since in Cartesian coordinate you are going to write as x comma y. I hope you know some basics about this one. So this is initial line, this is theta, this is r. So now what is the constraint here? R equal to constant. One of the coordinate is constant now. Just like z was equal to 0 in this motion, it was constant, isn't it? So similarly, one of the coordinate among two variables, one of the coordinate is constant, only one is variable. Is that okay? Now look at here, when it moves on a circle, we need only angle, we don't need that r, because r equal to constant we know. Is that okay? Again, this constraint that reduced the number of coordinate required in this way. Again, you need only theta. You can represent this one, this mass, the what you call state of that mass or point of that mass only by theta, because r equal to constant here. You don't have to mention that one at all. Are you getting my point? Thereby, this reduced coordinate. Now, what is the number of coordinate required? Only one, theta. Theta is sufficient to explain everything about the system. Alright. So now write the holonomic constraint definition. Now write the definition. Constraint which can reduce the number of coordinates. Constraint which can reduce number of coordinates required to explain the system. Required to explain the system is called as holonomic constraint. Constraint which can reduce number of coordinates required to explain the system is called as holonomic constraint. Yeah, what is the best example? So take as an example, you had three-dimensional motion. So usually you have to go for three-dimension and then you have to what you call define constraint equation. Okay, so z cap. And again, if I put z equal to 0, y equal to 0. So the constraint equation and number of coordinates is required is only one. Am I right? That's one of the examples. One-dimensional motion. Is that okay? Now let me take one more example. Yeah, this kind of restriction, it reduces the number of coordinates required. Am I right? But this kind of restriction is not. Yeah, we shall come to that one. That is non-holonomic. Okay. So one more example. So particle moving on a. It's very better to draw a circle first, then draw the coordinate. Is that okay? Again, it is draw a circle first, then put the center, then draw the coordinate. That's very better. X cap, y cap. Is that okay? A particle moving on, mass m moving on a circle, x comma y. Now actually both x and y are variable when it moves on a plane. Am I right? Already you have one constraint. I am not going to mention that one. What is that one? So it should be on the plane. That means z equal to 0 or z equal to constant. It should be on a plane, one plane. Okay. Now look at here. What is the constraint? This distance should be constant. Am I right? So I call this one as r equal to a. It's a constant. Okay. So now that's the constraint equation. Now look at here. Write this one as constraint equation. Or equation representing constraint. What is constraint equation? R equal to a, or root of x square plus y square is equal to a. So what is that one? X square plus y square is equal to a square. That's the equation of a circle, of course, obviously. Yeah, we are in the 2 dimension. We have one constraint equation. Whether it is able to reduce the coordinate? Yeah. So it is like that. It is like that. Just draw that one. What is that one? Polar coordinate. So polar coordinate. This is initial line. Mass m is here. So now a comma theta. Usually in polar coordinate you are going to write r comma theta as the coordinate of a particle. Am I right? So this is your initial line. So this is actually a. This is theta. R equal to a. Am I right? Now look at here. I don't have to mention this a. I can just mention mass. This mass is at this angle theta because radius equal to constant. Okay. But we need transformation to other coordinate. Okay, that's very important step in whole this theory. Okay, so what is this one? X equal to a cos theta, y equal to a sin theta. Am I right? This will transform it into polar coordinate. That transformation equation is also very important. Okay, the transformation equation is also very important. This is also holonomic constraint. Okay, not non-holonomic. This is also again example of holonomic constraint. Again, in case of pendulum also you can do the same thing because it is moving on one arc, a part of a circle. That's why only angle is sufficient to explain everything. Write one sentence on this holonomic. Usually, holonomic constraint equations contains equality. Contains equality. This seems to be a little ridiculous. Again, because non-holonomic constraint equation sometimes it contains inequality. That's why I want to make the what do you call it? Distinction. Are you getting my point? It contains equality. Equality means equation. Am I right? But again, that inequality. Other what do you call equation concerning with inequality? Inequation? No, no word like that, isn't it? Yeah. So holonomic constraint equation are usually they usually contain equality, no inequalities. Okay. No inequalities in the constraint equation. If there is any inequality, that cannot be constraint, holonomic constraint. Okay. Yeah, write down like that. If there is any inequality in constraint equation, that cannot be holonomic. If there is any inequality, that's the best word. Okay. If there is any inequality in the constraint equation, that cannot be holonomic. Over. Now just we shall take this non-holonomic constraint. Non-holonomic constraint. Constraints which cannot reduce number of coordinates can be called as non-holonomic. Constraints which cannot reduce number of coordinate constraint which cannot reduce number of coordinate is called as non-holonomic constraint. Example, particle constraint to move on a cubical box, suppose. Am I right? Or so rectangular box. X cap, y cap, z cap. X cap, y cap, z cap. Lx, ly, lz. Lx, ly, lz. If particle is confined in this container, then what is the constraint equation? X should be 0 to Lx, y should be 0 to Ly, z should be 0 to Lz. Constraint, yeah, it is a restriction, but it cannot avoid number of coordinates required to explain that one. Again, you need all three coordinates x, y, z to locate that particle. Am I right? Is that okay? So that's why usually this, okay, not always, usually this non-holonomic constraint contains inequality. Constraint equation contains inequality usually, okay. But there is one exception. Just read out Gostein, okay. So just read out Gostein. Again, let me give some more question, okay, on this one, constraint and all. So that is, when you just throw a disk on a plane, when you just what you call roll a disk on a plane, which is very rough plane, okay, so that it will purely roll. There is no slipping or skidding or something, okay. So it will purely roll that one on a plane. A plane is very rough. I mean, to roll you need friction, am I right? Are you getting my point? To roll completely you need friction. So then only it will roll properly, am I right? So now if you just roll a disk on a plane, actually, you can write one equality. You can write one equality. Let me show that one. So even though you can write one equality, the constraint equation contains equality, you can't what you call integrate that one equation, and what you do is you can't reduce number of coordinates required. So that's one exception. What is the exception? Again, so let us discuss this one. So just add this one in the example. Add this one in the example. A disk rolling on a horizontal xy plane. Let me discuss that one, okay? Because I need to discuss something else before this one. A disk rolling on the horizontal xy plane. Rolling on the horizontal xy plane. Constraint to move so that plane of the disk is always vertical. Okay, it's not like this. Okay, it's not like this. It should be plane of, so it constraint to move in such a way that plane of the disk is always vertical. A rolling, okay, just underline the word rolling. That's very important. Pure rolling, okay, yeah. So put it as other example. Okay, one more example, usually famous example is, suppose I have one fixed sphere, okay, I have one fixed sphere, big sphere. This is not moving. This is not moving, and this is not our interest. This is not our particle or something. But I have a particle here of mass m. I have gravity, and when you just displace that one from this point, what it will do? It will slide off. After some point, it will leave this sphere. Am I right? After some point, it will leave that sphere, leave the surface of the sphere. Now, how do you write constraint equation? One more example. Okay, non-holonomic constraint, and still this kind of question can also be solved in Lagrangian problem. Okay. That's very nice technique, variational kind of technique, okay? Yeah, look at here. How do you write that? Take this one as origin. Is that okay? So take 3 dimensions. So this is the origin of 3 dimensions. Am I right? Usually we take Cartesian coordinate. Now what is this one? R, distance from the origin. Now what is that one? R should be greater or equal to A, where A is the radius of the sphere. Am I right? When it is here, when mass is here, that radial distance that is greater than A. R should be greater or equal to A. Again, it's a kind of inequality. Non-holonomic constraint. Take it as other example. Under gravity. Okay, this shows under gravity. Now let me upload some files, okay. some exercise on this constraint. Okay, you have to classify. Yeah. Is it over? We shall solve this kind of problem. Okay. Next concept is what is this one? Wait a second, before getting into just generalized coordinate, I need to discuss one more, but that is very less frequent. I mean, that kind of case. So that is a renomic and scleronomic constraint. Okay, if constraint depends on time, then that is renomic. If constraint equation that is independent of time, then that is scleronomic. Is that okay? Just let me define that one later. But again, I am not taking time dependency here. For a time sake, let me not take time dependency. Little difficult to handle. So that's why again I am not taking those two categories. Again, read out the book. Okay. Again, let me define it later. Generalized coordinate. Okay. What do you mean by generalized coordinate? Any idea? Yeah. Number of independent coordinate. Am I right? Coordinates which is required to explain the system, but they should be independent. Am I right? The word independent is very important. Suppose let me take this situation. Suppose particle is moving on a. So particle is moving diagonally outward. Okay, shall I take like this? I have a origin, x here, y here, z here. Is that okay? I have origin. Particle is moving diagonally outward, so that the equation of the line is x equal to y equal to z. So shall I take like this? Now, in this motion of the particle, look at here. If you explain that one in three-dimensional coordinate, what would happen? They are dependent. They are not independent. Is that okay? Let me take the other example. Suppose let me take a particle moving on a circle again. Particle of mass moving on a circle. Am I right? X here, y here. You have two coordinates, x and y. Is that okay? So are they independent? No, they are connected by x square plus y square is equal to a square. X can be written in terms of y, or y can be written in terms of x. Am I right? This is it. Are you getting my point? Now look at here. If you want to explain this motion of a particle on a circle in Cartesian coordinate, then Cartesian coordinate will not become generalized coordinate. Why? How do you define generalized coordinate? Independent coordinate. Okay, coordinates which are independent of each other. So again, that is called as generalized coordinate. Is that okay? Now, if we transform this one, coordinate transformation, so then if you go for what you call polar coordinate, then again, so you are reducing that one, then it will be independent actually. Let me take some other example. Okay, let me take one more example like this. Look at here. Because here after transformation you will get only one coordinate. How do you say independent? You can say independent only when you have other one. Am I right? Let me take this one. So particle moving on the surface of a sphere. Particle moving on the surface of a sphere. So now how do you express constraint? I mean, it's not under gravity. Is that okay? Particle is somehow, suppose one metal bead which is moving on a one magnet, okay, which will be always attached to that one. Let me take that kind of situation. Okay, so particle which is moving on a surface of a sphere, I better to draw it here. Why? You will always feel this is downward. Am I right? Yeah. So again, this is origin. Now look at here. If you go for three-dimensional coordinate, that is r. Am I right? I mean, that's equal to constant. Again, if you go for Cartesian coordinate, what is the mistake? X comma y comma z. All three coordinates are variable. Am I right? All three coordinates are variable. When you go for Cartesian coordinate, all three coordinates are variable. Now look at here. Are they independent? Now look at here. This radius equal to constant. Am I right? R equal to A. That's your constraint equation. That says move only on the sphere. Am I right? So what is this one? Root of x square plus y square plus z square. Am I right? Root of x square plus y square plus z square. No, they are not independent. They are linked with this equation. Or I can write like this: x square plus y square plus z square is equal to a square. Am I right? In three-dimensional coordinate, I can write like this. Am I right? Now look at here. They are not independent. So now Cartesian coordinate cannot become generalized coordinate for this problem. Particle moving on sphere. Now what can become generalized coordinate? Go for spherical polar coordinate. Am I right? Go for spherical polar coordinate. Now look at here. If you go for spherical polar coordinate by the transformation equation x equal to r cos theta sin phi like that, isn't it? So we shall take that coordinate geometry. First we shall go through some example. Okay. So now look at here. So now if you go for what you call, again, what is the rule? Whose mass is here. Is that okay? So x, y, z. Is that okay? So now it's xy projection. If you project on xy plane, then this will be phi. Is that okay? So this is r equal to a here. This is theta. Theta angle with the z axis. Am I right? So now look at here. This should be represented by r theta phi. Position of that mass should be represented by r theta phi. Now look at here. R equal to constant. Am I right? R equal to constant. So now what is this one? Theta and phi. Am I right? Theta and phi are enough to specify motion. Am I right? Motion of the particle. So that's why look at here. You had three coordinates. So it is reduced to 2. And they are independent now. They are independent now because you don't have equation connecting theta and phi again. Is that okay? So now it is reduced and these two are independent coordinate. Again, there are no dependency between theta and phi. Now this becomes generalized coordinate for this particular problem. Is that okay? So this is most important concept in this one because choice of generalized coordinate solves the problem 50%. Other 50% is to solve differential equation. Is that okay? Proper choice of generalized coordinate will solve problem 50%. Is that okay? Now let me just proceed with this one. So take this one as an example. Wait a second, let me give the